So down here in 9.5, I have a summary of the steps. And this is the minimum you need to do to really do the whole process. In this minimum approach, you can do it in just a couple minutes, even though it's a lot of boxes to check and answers to put. It doesn't take long. And then if you step back and you want to really visualize it and understand it, you can do a little more than just these minimum steps. And so I'll talk about kind of the quick and to the point version. And then with each of these, I'll take a step back and try to make sense of what we're looking at. So starting off with hypothesis tests about population mean, we are going to do these 5 steps. Make a statement regarding the nature of the population. So you take a claim or a statement about the population mean, turn it into your null and alternative hypotheses. Call it the setup. So these 5 steps, just to really simplify things down, is a setup for your null and alternative. Second one is requirements. Third one is run the numbers, crunch the numbers, use Staplet to find your T or Z test statistic and your p-value. So that's, we plug in what we know, it spits out these numbers. These are going to describe the sample as it relates to the null hypothesis. So we figure out sort of a degree of likelihood of our sample in the p-value if the null hypothesis were true. So if that p-value is tiny, then we're saying it's not likely that the null is true, and we have this other option, the alternative. So it's kind of like we start by assuming the null is true, and then if we get an oddball result, we say, that probably was not a good assumption. So what's the other thing that we could assume? And that's why we have this null and alternative, like 2 option system. It's got to be either one or the other. And then that is sort of what I just described as the decision. And lastly, instead of just a statement about the null or alternative, we bring it back to the original problem, contextualize it. That's what we mean by conclusion. So that's a real basic description of the 5 steps that we're looking at. And in the first example, right here, and so I wrote all these problems, kind of trying to use somewhat similar situations that you'd find in real life. You have an airport claiming that their delay times are under 10 minutes. So right away, we see a statement about the population. It's a left tail, a less than sign. It does not contain an equal sign, so it will automatically be the alternative, and the null will get the equal sign. And so that's what I've got in step 1 there. And as we go through these examples, I'll just kind of sketch sort of in my head what I'm picturing as we do each of these. And I think that can kind of help you to sort of get that picture with it that you might not sort of readily visualize. So we start with a claim, and the claim is that mu is less than 10, which becomes our alternative. So population mean less than 10, null hypothesis default gets the equal. So right here in my head, what I'm picturing is a distribution of samples and average of samples, and I've got to put something in the middle. And so I see an equal sign here, and I say, why don't we just assume that that equal sign is true? And now if we're far enough to the left, that will look good for the claim. So we would want our sample to land here, so that basically our plus and minus margin of error would put that whole confidence interval under 10 minutes. That's sort of how we visualize that first setup. So then I check the requirements, and I note that there's an alpha of 0.1. So that will be the sort of cutoff for, I want to be in that left 10% of possibilities. to really consider myself far enough to the left. And the requirements are for this one, we need to have a simple random sample. It doesn't say specifically, honestly, it should. I think that might have just been something I missed when I typed the problem. We should have either a normal population or a sample of at least 30. We've got at least 30 because we've got 100. And then we shouldn't have a sample that's more than 5% of flights. And I think there's going to be, thousands, tens of thousands of flights, so that won't be a problem. So that's just kind of thinking about the requirements of the distribution. Now we go to run the numbers. We go to Staplet. So what we'll have for a t-test, couple of options to get there. You can, in general, you can find all this traditional inference down at the bottom. The intervals and tests are called inference because we're trying to infer information about a population. So infer is to deduce or conclude from evidence without sort of the entire story. And so you can look down there, but what I tend to do is just pick either one categorical variable single group or one quantitative variable single group. We've got a quantitative variable. We don't have raw data. We've got a mean and standard deviation. So step 3 is to, and so my 2 is requirements, and I'm just going to put a check mark there. Check the requirements. We met those. 3 is where I'm going to run the numbers. What I tend to do there is kind of note from the sample what I've got for my sample information. I've got n equals 100, x bar 8.5, s 11.1, and that's what I'm just kind of putting down here to label those with the right variables. And then I'm plugging them into Staplet, one quantitative variable. And I don't have many options for this. All I can really do is an interval or a t-test. We're not looking at these other two. That's called chi. It's a Greek letter. We're just doing a t-test for the population mean. And then we look at the alternative hypothesis. This is important for calculating the p-value. If it's a left or right tail, we just look at the area to the left or right. If it's a two-tail, we look at that area and double it. So it's all happening kind of within the system, but we have to tell it what kind of tests we're doing to make sure that it does the right calculation. So this is a left-tailed from that less than sign, and it was hypothesized that it was less than 10. So now I get the two measurements I'm really looking for. I get a t test statistic. In the notes, you'll see that also is called t sub 0 or t naught or t null. Just essentially that has that little 0 subscript next to it. And that's all the way back here in the second section. Since I skipped 9.2, that would be 9.3. And I talk a lot about that t test statistic in that video there. You can calculate it yourself using a scientific calculator right here. It's measuring how far the sample mean is from the population mean and dividing by the standard error, which is essentially how spread out those tick marks are on the distribution. It's just, if we were to measure a standard deviation in this curve, this is what it would be. So that t measurement tells us a number of standard deviations. We are 1.351 standard deviations below the mean. That's not that unusual. If I kind of draw my curve again now, I'm putting that population mean of 10 in the middle, but instead of thinking about, sample population mean, I'm just going to make it a t curve this time. I'm going to standardize it, meaning right in the middle is 0. And then I go down by 1. Kind of when you get to the tail, you should be about -2. -1 should be about halfway down. That's the inflection point where it's a little bit flat there. There's one, there's two. So this is why we really like to standardize things, because then we don't need to think about like putting a 10 in the middle and figuring out where an 8.5 would need to land here. Now it's very easy. We just go 1.351 tick marks over. So a little over 1 1/3. So there's the first one, and then about 1/3 means my sample lands about here. Not that unusual. We tend to think of -2 as being kind of where things start to be unusual, but for the process, we really don't. We would need to know a critical value for that. So we just kind of think about t in terms of visualizing it. But when we want to go make the decision, we use the p-value. So the p-value actually measures this area. Measures the area to the left of the sample. And that is outputting a p-value of 9%, 0.09. And the decision, we have to make a decision whether we want to reject H0 or fail to reject. And that is specifically listed here in 9.4. Reject the null hypothesis if the p-value is less than alpha. That's the situation we've got. We've got an alpha of 0.1. We've got a p-value of 0.09. So that p-value 0.09 is less than alpha of 0.10. And so to visualize that, essentially what happens is we shade a different color for alpha, and we ask ourselves, are we going to be shading, past that value? And we actually are, just a little bit, about 1% right here goes beyond that. And so we see that our alpha region, or we call that the rejection region or the critical region. I like the term rejection region because if it's in the rejection region, you're going to reject the null hypothesis. So actually, alpha was the key piece to make the decision. If someone decided, I'm okay with a 5% level of significance, then the sample doesn't end up in the rejection region. If they want a 10% level of significance, it does. And so that's going to be included in the conclusion what our level of significance is. So the decision, like I said, we're going to reject the null hypothesis. And essentially what we're saying is that number that we put in the middle, we don't think it's correct because our sample was too far to the left. It was sort of in this unusual space on the left side. And then the final conclusion, what we'll use is that decision. And so our decision was to reject the null. We had a one-tailed test. So we're going to say the sample provides sufficient evidence to conclude that the value of the parameter mu is, and in this case, it was less than 10. So let me write that out here. Or maybe it's better, let me just type it because my handwriting is not the best in here. So the sample provides enough evidence at the alpha equals 0 point level of significance. I don't know why the size of this is getting bigger, the text, but let's see if I can, nope. So I've kind of brought it back to the context of the original problem. So we want to think of it as if we land in the rejection region, or if we have a small p-value, then that's a lot of evidence. Another way you could look at it is if T is extreme, like beyond 2, beyond 3, sometimes T is beyond 5, like negative 5.2. That means you're 5 standard deviations away from that assumed value. That's not going to happen much, and your p-value would be almost 0. So if you have a tiny probability of this result, then that's a lot of evidence against where we put the middle of that curve. In fact, what we're kind of saying is we're saying we assumed the middle was 10, but we actually think we should maybe slide it down a little lower and put it at maybe like 9.5 or 9. And we're saying, you know, if we were to redraw the curve, we would actually draw it lower, and that would put our sample more in the middle. And that's ultimately what we're going for, is we're trying to really show that those flights are, you know, delays are under 10 minutes, and our sample is well enough under 10 to support that. So that's how that first problem is going to look in the notes. Going back to look at what I've got here. Example 1, left-tailed test here. So I had my t-value and my p-value spit out. Just took note of those. Then I compared the p-value to alpha. It was smaller. That means I reject the null hypothesis. Used that to come up with a conclusion. So the additional information at the bottom is kind of that missing information that you don't see. I graphed it. So this vertical bar is the sample, and that shaded region is the rejection region. It can get pretty messy when you're trying to shade both the p-value and the alpha. So that's kind of why there's this other way to visualize it. Just looking at the sample as kind of like plotting a point. I put it as a vertical bar. That's our sample. That's our negative 1.351 t-value. Don't worry about y there. And then our shaded region is 10% there. And you can see that t-value for that cutoff is 1.29 to get a 10% approximately. I might be able to get a little more precision and get that a little more accurate, but that would do it. And so the notation for that critical value is we put the tail size in the subscript. So we're saying a t-value at the edge of a 10% region on the left side, negative side, is at negative 1.29. So we're putting the cutoff for the rejection region at 1.29 on the left. We got negative 1.35, so we're a little bit past that. We're in the rejection region. We reject the null and say, yeah, we've got sufficient evidence. So that's putting it all together for that first example. The second one, kind of boil it down just a little more from that, kind of go through it a little bit quicker, a little bit more directed. So right from the beginning, we're looking for a statement about the nature of the population. We have a previous study that says it is 5'9" or 69 inches. We are trying to collect evidence to see if it's changed. We don't know if that's an up or down change, so that creates this two-tailed test. We're saying it's either equal to what it was before, or it could be above or below that, or not. We would say not equal to that. We check the requirements. Here we have a sample. Again, it should say simple random sample. I think that's something that I just missed when I wrote the problem. So I will add that to all of these problems. Should be a simple random sample. We should have either a large sample. Now here I've only got, let's see, 3, 6, 9, 12, 15 adult males. That's a small sample because it's under 30. It needs to be a normal population. And we do have that up here in our problem. So we're going to get away with the small sample here because we have the predictability of a bell curve from the start. So those are kind of my requirements. And then I go into Staplet with my data set. So here I'm just going to copy paste into raw data. See the dot plot. It's nice to look at the box plot. If there's any outliers, sometimes we won't proceed because that will really give us an inaccurate view of the population. It's not that the outliers are invalid, it's just that you're going to have a measurement for the standard deviation that's much more inflated by that outlier, unless they're kind of like perfectly even on both sides and stuff like that. But what we want is the inference. So we go down to the bottom. This one we got a lot more options than when we did just the mean and standard deviation. And that's because it's just giving you all those sample statistics. So you could take note of the mean there, the standard deviation. But what we want to do is a one sample t-test. And this was a two-tailed with a hypothesized mean of 5'9", which is 69 inches. So this is a very unremarkable t-value. It's only about 1 standard deviation from the mean. It's a large p-value. So here's the kind of visual at the bottom. We can see with a 5% level of significance right here, we're splitting that into 2 regions of 0.025 on each end. And that's beyond 2 standard deviations to get there, 2.1 approximately. We're only at 1 standard deviation from the mean. So think of this, I kind of like the two-tailed test because it's more like a confidence interval. We put a value in the middle and we have a plus and minus margin of error that gets us out to that tail. And this is just kind of sampling error. We could easily land in this region, and we will land in this region 95% of the time because we've excluded the 5% on the extremes. And so we're saying, look, we're pretty close to the middle. We're not right on the middle, but we don't really expect to be all the time. This is within the margin of error for just sampling. Sometimes your sample's a little high, sometimes it's a little low. So this decision, the p-value's bigger than alpha. We see this 32% p-value that's more than 5%. That p-value would be if you shaded to the right of this and doubled it to make it reflect that reflection across. So you have about like 16% on this side, 16% on this side, 32% total. And that way we can see we're shading a lot more than we would be if we were in the rejection region. So if we fail to reject, this conclusion is very similar. We just say we don't have enough evidence. We either do have enough evidence to say, you know, we're to the right or we're to the left or we're, you know, different from, changed from, or we don't have enough evidence. If we're not in the rejection region, it's not enough evidence. So that one I kind of went through a little quicker. I think when you're doing the homework, you don't necessarily need to visualize it. I think that can add a lot of steps. You have some steps to find the critical values. But if you did want to do that, I really talk a lot about the visualizing in 9.3, that section. So when we go to qualitative, categorical, we're looking at proportions. So we're going to have like a fraction of the group that meets some criteria. We're going to have a claim about that proportion. You have to watch for words like majority. That's something that doesn't come up with quantitative. Majority means more than 50%. But it also could just be like, you know, more than 15% or not equal to 40% or different things like that. The requirements here, we need to make sure it's not too skewed, which is this n p0 1 minus p0. So we take that h0 p, we find its complement. This one's 50-50. And then we multiply all of that by m and make sure that's at least 10. So we're good there. And we should have a simple random sample. Looks like I got that in that one. And then we shouldn't have more than 5% of the population sampled. And I think with your homework, you should meet all the requirements every time. Otherwise, like I said in class, if you don't meet the requirement, you can't do the problem. So I'm going to try not to ask you a question that you can't actually answer. But we just want to make that check as part of the process. So in this one, it is a just summary of the votes. It's already been grouped we would start with a whole list of votes like Alana, Abby, Lincoln, Abby, Alana, just imagine a bunch of random votes. We tally them up. So we have kind of summarized data here for the one categorical. That's going to be counts and frequencies. So we just need to put those three qualities or observations that we have. Oops, I got rid of my my notes. Let's see, where was I? Here we go. So we have 121, 96, and 15. Six, 15. We'll do the analysis there. We don't really need to pay too much attention there. Here we're going to have the winner at 52.2%. And the claim and the problem is that she won with a majority of the vote. So we're just really trying to see, is her vote far enough above 50 that we're beyond sampling error, that we can really have some evidence that she's over 50. So if our sample had her right at 50.1%, we'd say, this is not that big a sample. This could easily be an unusually high sample, but she actually lost. So we're just trying to make sure like we're far enough above 50 to be in that right tail that we have here. And we run the numbers now on a one sample Z test for Alana, right-tailed over 50. And I want to type 0.5, or I want to type the decimal here every time, and it'll give you an error. So this one, I really wish they would actually have a percentage sign there, but it says what percent. So that's how they're doing that. So we got a very unremarkable Z. Think of it, like I said, 2 or -2 or beyond is kind of somewhat more remarkable. This is going to happen a quarter of the time if she was right at 50%. So we're really not far enough above it. We have a big p-value in this one, 2.56. We're comparing that to an alpha of 0.1. The p-value is much bigger than alpha, so we won't reject the null hypothesis. To visualize it, you can see here, our sample is only a z-score about 2/3 of a standard deviation, about 2/3 of the way from 0 to 1. We're right in the middle bulk of the distribution. For our 10% critical value region, the edge of that is going to be past 1.282 standard deviations over here. So we're not in the rejection region, failed to reject the null. We don't have enough evidence to support that she won the election. So you can think about, now she may have won, I mean, we may have evidence that she got enough votes more than the other candidates to give her, the most percentage of the votes or the biggest share of votes. But just to answer if it was more than 50, we don't have enough evidence there. Think about the election project. In that one, it was reported that Paul won, but he actually got less than half the votes. So there, we couldn't do any kind of hypothesis test supporting his win. We would need his votes to be significantly above 50% to kind of support that outcome. And now we get to the raw data version, similar kind of problem. Here, a company claims that their absence rate, absenteeism rate has changed from 7%. So we're saying it's no longer 7%, it's not equal. We've got raw data, just present and absent counts. And it kind of feels silly to have raw data on these problems, because it's like, why didn't you just tell me how many of each you had? But I wanted to give you an example of that. So I'm going to copy that data set. And go back to raw data in this categorical and paste that there. So right away, it's going to summarize it for me. 139 absent or present employees, 21 absent employees for 86.9% present rate, 13.1 absent rate. And that's the one that the claim is about. The claim said that it's changed from 7%. So I do my check. It was 100 and wait, well, that's the wrong one. It's 160 total employee work days that we're looking at there. And then I take the 7%, I take the complement, that's 93%, multiply it by that number of data points, and I just passed 10. So it does meet that requirement. Now it's pretty skewed. At a 7%, 93%, we're way off of 50-50. Anytime it's skewed, you're going to need a lot bigger sample. So if it's 50-50, you need a sample of 40. As we vary from 50-50, we go up from 40. If it was a 99%, 1%, we would need a much larger sample. Otherwise, we meet the requirements. This one is a simple random sample. We don't expect that to be more than 5% of all work days for all employees. Then we need to run the numbers. I've already got the data in. I just need to do my one sample z-test. I'm looking at the absent rate this time. Make sure you pick the right wording for success. It's a not equal 7%. So that's just that whole number 7. And we're 3 standard deviations from the mean here. So this is a remarkable sample. If the null hypothesis were true, this would be very extreme and would only happen 0.2% of the time. So this is this last example is one where we are far from the middle. So if we assume here that it's 7% in the middle, our sample doesn't look very likely. So that's a lot of evidence against that 7% rate. And we could say with this sample, we even have evidence that it should potentially be higher than that, maybe closer to that 13% that we got. And so just to kind of wrap it up, we look at the p-value. That's less than the alpha, which was 0.01. And then that gives us reason to reject the null hypothesis. Rejecting the null hypothesis is equivalent to sufficient evidence. So I like that term, beyond reasonable doubt. What's reasonable doubt? It's the distance from 0 to the edge of the shaded region, and we are literally beyond that number. So we're beyond reasonable doubt. In a courtroom, that would be enough evidence to convict. That's what we've got here. Just a note, when you do the formula for this z test statistic, so here where I get this 3.03, Staplet will output it with precision. When you do that by yourself, if you do want to type that in by hand, that's what that formula looks like. It's a p hat minus the null hypothesis p divided by the standard error. I typically will use a fraction here for that p hat. It's something that you don't need to worry about unless you kind of get into the weeds of it and want to really look at graphs and comparisons. But I thought that was important to note that for p hat, we do have a percentage for that, 13.1, but that may be rounded. And so using a rounded number for later calculations can actually give you some just rounding error. So what you've got now with this video, with this demonstration, is an example of 4 different types of hypothesis tests. You've got 2 of them that have to do with the t-distribution and the mean. You have 2 of them that have to deal with z-distribution proportion, so quantitative for the first 2, qualitative for the second 2. And I've also tried to give you examples of different scenarios, like here we failed to reject, here we failed to reject, and then in the other 2, you have enough evidence to reject that null. One on the left, one on the right, one on the left. So lots of different scenarios, and there's a lot of different ways it can go.